welcome to our official start of Big Data for today. And now let me share my screen. So today we're going to talk a little bit more about indexes. We'll finish the material that we didn't quite get to last week related to our the homework assignment. And then we'll start talking about full text search in Postgres. So we'll see exactly what that means later on, but basically sort of Google style searches where you type in some text and it searches an entire text document for the contents rather than doing like an exact match. So as a reminder, the homework that was originally due last week, I've extended it until this Sunday. And since we haven't finished talking about all the stuff for that, I haven't posted a new homework yet, but I'll post that later this week. Any questions about the last homework or really anything?
I do have a few questions, but we can talk about it at the end.
Okay. Yeah, the for those true and false questions on the homework, there's quite a lot of them, and so definitely would make sense to have questions on them as you're working through them. One question that came up is for the final exam, will you have that many questions on the final exam? And the answer is no. This is more, think of these questions as like a bank of questions. It won't be exactly drawn from this set for the final exam, but they'll be very similar. They'll probably be on the order of between 10 to 20 questions, like in the true or false category in the final exam. Okay, so let's talk a little bit more about indexes. And the first index that we'll talk about is the hash index, comparing it to the B-tree index, mostly to remind us about what we talked about with the B-tree index. And then we'll get to those join strategies down here, joining tables, which was the key last thing that we haven't talked about yet. So the reference for this is again from that Haber webpage, that Russian webpage, and it goes into a lot of detail on hash indexes. The way to think about hash indexes as they compare to B-tree indexes is if you, like an analogy with your data structures class, that a B-tree index is to a balanced binary search tree as a hash index is to a hash table from data structures. I know there's a couple of you who took data structures with me last fall, and because of the coronavirus situation, we actually didn't really fully cover the hash table data structure. That was the thing that we had to take out because of the missing weeks. And so for those of you in that situation, it might make extra sense to read through this link right here about the details of how hashing works. So yeah, the key high-level idea is that, again, trees, the balanced binary search tree, it reduces our search time from linear down to log in the worst case. And then the hash table gives us constant time, but that's not worst case constant time. That's what we'd call amortized average case time. And so slightly different meanings here and slightly different runtimes, but the runtime of log in is essentially constant. That when n is in the billions or the billions of billions, log in is still only 10 or 20, so it's really, really small. The dictionaries that are the default dictionaries in most programming languages, so Python and Java in particular, use hash tables as their implementation, but C++ is a little bit different. They use AVL trees in their implementation. So in Postgres, the database world, when do we use hash indexes? And the answer is almost never. If somebody's using a hash index, then they're probably doing something wrong. And the reason for that is we'll see that it can sometimes be like very, very marginally faster than a quality search or than a B-tree index for like your standard quality where condition. But it's actually very rare for it to be faster, and it supports so many fewer operations that the B-tree is just the standard thing that everybody uses all the time. So even though most programming languages use hash tables for their things instead of trees, in database world, basically never use hash tables and always use the B-tree index. So real quick, visit this link right here. That's this web page right here. And this is a picture overview of what's going on in the hash index. And each one of these buckets is one of the page files, just like we had on the tables or the B-tree. And the way we assign a tuple into a bucket is we hash the corresponding whatever the key is that we are creating the index on, and we put it in the corresponding bucket. So because there are multiple multiple hashes for multiple different values can hash to the same thing, go in the same bucket, you're going to get collisions, and you'll have multiple things inside of a bucket. So this is just the sort of standard hash table sort of implementation. And sometimes, so if you have more things in a bucket that can fit in a page, then you'll have like an overflow list where things get stored. And that's, if you have a good hash function, that's incredibly unlikely to happen, but it is something that can happen. So limitations, why people don't use the hash index. First of all, it only supports a quality search. It doesn't support range search like the B-tree does efficiently. It does not sort the results like the B-tree does. We saw last time at the very end, we were talking about aggregate strategies, and there were two aggregate strategies, the hash aggregate and the group aggregate methods. And the group aggregate method was the faster one, and it required sorted input in order to work. So if you have a hash index, it's not going to make the group aggregate happen for you. But if you have a B-tree index, it will make the group aggregate happen for you. Another sort of limitation of the hash index, and this is just an implementation detail, but currently the way it's implemented in Postgres is that the hash table will grow in size as you add more things to your table. That makes sense. But as you delete things from the table, the hash table will never decrease in size. And there's no way with vacuuming or anything to get it to decrease in size. So that's just an implementation detail, but it's one of the reasons why people don't really use hash indexes. There's also no support for index-only scans. So we saw last time that there were 3 methods for using indexes: the index-only scan, the index scan, and the bitmap index scan. Of those 3 methods, the index-only scan is the fastest because it doesn't have to reference the table at all if you've been vacuuming. But in a hash index, because we only store the hashes of values, we don't store the values themselves, we're guaranteed that we always have to refer back to the table to go get the actual value. So that's why it doesn't support index-only scans. It also does not support multi-column indexes, and if you go back to even older versions of Postgres, there's even more limitations than this. So lots and lots of reasons why people don't use hash indexes. So the runtime, really quick. So we're looking at, every time we were talking about an index, we're looking at 3 things about the runtime: the number of table pages accessed, the number of indexed pages accessed, and the total number of comparison operations that we do. Again, for most operations on a database, I/O operations, disk accesses are the most, like the bottleneck of our operations. And so usually we care more about the table pages and the index pages accessed than we do about the comparison operations. That was the reason why in the B-tree table, having a large fan out was the thing that we wanted. For the hash index, the total number of table pages accessed is the same as the B tree. The thing that's different is the index pages that are accessed. Here it's O of k divided by b instead of this formula that we had over here for the B tree index. Recall that n was the total number of entries in our table, the total number of rows. B was the fan out. So this was the number of steps that we needed to get from the root of the B tree down to the leaf nodes of the B tree. And then this was the total number of leaf nodes of the B tree that we had to access. K was the number of items that we're going to return. And again, B is the fan out. So if we have an equality search, then K is just going to be 1. But if we have an inequality search, or if there's multiple entries that match the whatever value we're searching for, then K could be greater than 1, and we could span multiple pages. So this is the sort of theoretical reason why you might prefer a hash index over a B tree index is you get rid of this term right here. But again, on practical pages, because B is on the order of like 500 for a B tree index, typical B tree index in Postgres, log 500 of even a billion entries in your table, that's only going to be 3 or 4. And so it's only an additional 3 or 4 pages that you have to access compared to a hash table, which is not that much. There's one important optimization too that we haven't really talked about yet. This optimization is called the buffer cache optimization. And this is a really complicated aspect of the Postgres database system. Every database is going to have something like this inside of it, and it's one of the things that makes the internals of the database really hard to implement. Effectively, what this optimization does is it stores the most recently accessed pages in memory. So rather than having to go back to the disk every time you want to access the same page over and over and over again, if you're just accessing that same page, Postgres will store that in memory for you so you don't have to access it multiple times. Because the top levels of trees, like the root of a B tree, is going to be accessed every time you access a B tree, that is one of the nodes that's going to be stored in your buffer cache. And so you're not actually going to pay a disk IO penalty for accessing that. Let's see. So this buffer cache optimization, it makes lookups much, much faster because we can essentially take away most of this penalty over here on our index accesses. All of the upper levels of the B tree will be stored in the buffer cache. But the disadvantage is that it makes insert, updates, and deletes much, much more complicated to implement internally inside of Postgres. And in particular, the ACID guarantees, making it so that whatever's stored in memory is guaranteed to be exactly what's on disk. So that if there's a power failure or your computer catches on fire or the program just crashes for some reason, that you're not going to lose data. And Postgres manages all of that for us. If this were like a CS-focused database class, we would talk a little bit more about how it's doing all of this internally. But for our more data science applications, it's just enough to know that this thing exists. It's complicated. We don't have to care about it, but it's magically making all of our queries faster for us. Let's see, there's a really famous joke in computer science. It's probably the most famous joke in computer science. And the joke is there are 2 hard problems in computer science: cache invalidation, naming things, and off by 1 errors. So the off by 1 error is something that you encounter in your first programming class. Naming things is also something that, like, relatively simple. Even non-programmers can discuss, like, oh, should Postgres be called Postgres or something else? But cache invalidation is actually, in some sense, the hardest problem in computer science. There's lots and lots of ongoing research in the database world, operating systems world, hardware researchers. All of these people are thinking about how do you implement cache systems like this buffer cache optimization efficiently, and nobody has like a good universal solution. And given certain like assumptions, it's possible to prove that there are no good universalist solutions. So yeah, it's a important optimization that happens inside of Postgres, but if you want to read more about the details, here's another link to that Haber webpage by that same Russian author. But for our purposes, you just need to know that it exists and it makes things faster. The last thing about the hash index is how, like, the syntax for actually creating it. The only difference between the syntax between a hash index and a B-tree index is this part right over here, that if we were to delete what I have highlighted right here, then it would, Postgres would default to using a B-tree index. If we, whenever we try to specify the exact type of index that we use, however, we put this using clause in here and then the type of index right here. So if I wanted to change this hash to B-tree, I could do that as well, but it defaults to B-tree, so I could also delete these two words right here. Are there any questions about the hash index at all, or how it relates to the B-tree index?
Yeah, so I was wondering what the fan out means in terms of a hash index.
Yeah, that's a good question. This B, the fan out in the hash index, what does it mean? It's the size of the buckets in that you have over here. So here, the way this is drawn, there are 3 sort of entries per bucket, and so your B value would be B3 in this case. Any other questions about the hash table? Okay, then we'll move on to joining tables, and this is going to be the main meat of what we'll talk about today, the most important part. And so there's 3 strategies for joining tables. We'll talk about them in a second, but recall that a join is anytime you have something like this. So these strategies are for when you have selecting some columns from any table A, and then these strategies work no matter what type of join you are using, whether it's a left, a right, a full, an inner, a cross join. It doesn't matter. They all use these same 3 strategies. And then so we're joining table A to table B, and then we have some join condition that we're joining the tables on. So this link right here is the reference that we'll use for joining. And I want to visit that just for a second. And so at the top, they have sort of a description of what the algorithms do. We'll do a little bit more detail than they have up here in the lecture notes. But this table here is really important. It's like the main summary of what you should take away from our discussion today. That it sort of talks about the key differences between each of these algorithms and when it's a good strategy and how you can create indexes that will help with these joins if you're using one of these joins. For the true and false questions related to joins, it's almost all from this table. And if it's not from this table, it's from this a little bit more discussion down here about the details of the entries in that table above. Let's see, so the final exam is going to be a take-home exam. You'll have open note access to everything. So one thing that I'm not going to do is I'm not going to ask you to reproduce this table verbatim, but if we were in an in-class environment and then I would have just a quiz where you have to memorize this table and reproduce it. So it's like the fundamental thing to take away. yeah, with our discussion of like what the algorithms actually do, if you understand those, the table should be like really easy to be able to reproduce. Um, but I do recommend that you're be able to reproduce it without looking at it. Okay, so there's three types of join strategies. The first one is a nested loop join. And scroll down, there's a hash join and a merge join. The nested loop join is sort of the most general one. It works in all scenarios. It's sort of like the equivalent of a table sequential scan for joins, because it's something that you can always do even if you have no index. So if you don't have an index, without an index, the pseudocode looks like this, that you have two for loops. So looping over each row in A. In all of the pseudocode here, I'm using lowercase letters to represent an individual row, and then the uppercase letter to represent the table itself. And the lowercase a is a row from uppercase A, and lowercase b is a row from uppercase B. And so we have these two for loops looping over the entirety of both tables. And inside we have this if condition. If we satisfy the join condition, then we output the joined row of A and B. So it's hopefully intuitive that this is an algorithm that can work in any situation. We don't need anything special in order to do this, and it's going to give us the results that we want for our join. The runtime is sort of quadratic, m times n, because we have two for loops. And here m is going to be the size, the number of rows in table A, and n is the number of rows in table B. When we're talking about the runtimes of these join strategies, I'm not going to be as specific as I was for the index strategies. I'm not going to like break it down between the index operations and table pages and the actual computation independent of IO, because it's not quite as useful in this case, but we could be a little bit more precise with this if we wanted to. So this is, yeah, a nested loop join without an index, the most general strategy that we have. If we do have an index, we can take advantage of that in the nested loop join. And the idea is that the purpose of this sort of inner loop right here is to find all of the rows that happen to satisfy whatever our join condition is. And if we had an index on the B table, then we could replace that for loop, replace what is essentially a sequential scan of the table B right here with some sort of index scan on the table or on the index. It could be an index-only scan or an index scan or a bitmap index scan, depending on what is appropriate for our particular table size and the type of index that we have. But either way, that's going to reduce our runtime from this sequential scan linear time over B down to a log n time. It's a logarithmic over B. And so a drastic reduction in our runtime from mn down to m log n. One other sort of subtlety about the nested loop join is that remember that joins in SQL are commutative. So that means this query right here, when we have from A, join B, we could rewrite that as from B, join A, and using the same join condition, and that's the exact same query, gives us the exact same results. So because of that, we can effectively reorder these for loops, whichever way makes most sense to do. And we can reorder this right here so that we're looping over table A and using the index on table B here. But down here, we're looping over table B and using the index on table A here. So that gives us a different runtime of O of n log m instead of O of m log n. And so if you are in the case where you have to use a nested loop join with an index, then whichever table is smaller, that's the one that's going to be the outer index or the outer loop right here that you have to do the full work for. And then whichever one is larger, that's the one that you'll do the logarithmic work for using the actual index itself. Are there any questions about this nested index join or nested loop join? Okay. So because this type of join is so general, it is the most commonly implemented in other database systems. So for most variants of MySQL, for example, this is the only join strategy that they have available to them. Oracle has a similar set of join strategies as Postgres, though, that more than just this nested loop. So we'll take a look at the next join strategy, the hash join, next. The hash join, you can't use it in all situations. It has these 3 requirements. The first is that our join condition must be an equality condition. So our join condition, again right here, the vast majority of joins that we're doing is an equality where one column equals another column. But it is possible to do a join where you have one column is greater than another column, or using an inequality like that. I've personally never seen an application where that's actually been useful, but it's technically possible. And so on a join condition like that, you would not be able to use a hash join. So this is sort of a technical condition, doesn't really come up in practice. In order to explain what these next 2 conditions are, let's talk about the pseudocode, what it looks like. So here, the very beginning, we don't start right away into our joining. We start by building a hash table on the join column on B, table B. So this is whatever column we're looking at in our join condition up here, we'll build a hash table on that. And that hash table is effectively exactly the same as the hash index. Then for each row in A, so looping over just like we did above, if our join column is in the hash table, then we have to recheck to see if B is in B due to hash collisions. And assuming it is, that there was no collision, then we output the row. The way that I think of a hash join is that it's basically just like a nested loop join, where the inner condition right here is using a hash index, and we're creating that hash index sort of on the fly. I guess the nice thing about the hash join, though, is that we don't have to have that index sort of pre-built available to us beforehand. It can create that for us automatically. The disadvantage of that is that there is some overhead to building that hash table at the very beginning. And there's a parameter called workmem, stands for the amount of working memory that every process has. And your hash table must be able to fit inside this working memory parameter. The difference between this hash table and the actual hash index is a hash index is going to be stored on disk. It's going to be subject to all the ACID guarantees about if the program crashes, the index will still be valid. This hash table is only going to be stored in memory, and so it's much faster to create and to use, but then it must fit inside of this parameter. I think by default, this parameter is very small in Postgres. It's only 2 megabytes. But if you consider that the hash values, they're going to be 4-byte integers, and you can fit about 500 million 4-byte integers in 2 megabytes. So it's still like a pretty decent size table that you can do a hash join with. If you have tables bigger than 500 million rows, which is certainly a normal thing to have happen, then you just increase this working memory parameter from 2 megabytes up to 10 megabytes or 20 megabytes. And These values, like 20 megabytes, is basically free on modern computers. So this is not a difficult thing to increase. It's not an expensive thing to increase. The runtime for this algorithm is, so we have to build this hash table that takes time linear in B, so O of n. And then we loop over each row in A. So this is O of m. And then everything, each one of these lines inside of this for loop, each one of these lines takes constant time. The most sort of expensive of these is actually checking if something's in the hash table. But doing that check is only constant time because it's a hash table. And so we have O of m for this entire for loop right here, and O of n for this hash table right here. So our runtime is m plus n. This is potentially smaller than this up here, and it's potentially larger than this up here. Sort of depends on the exact values of n and m. If you have one table that's really small and one table that's really large, then the nested loop join with an index is going to be better. But if you have both tables being relatively large, then the hash join is going to be better. One last subtlety about the hash join is that it can't take advantage of limit clauses very well. Let's say we have a limit one clause in our select query, so we only need a single row out of our join. Well, in that case, we still have to build this entire hash table up here. And so we still have to spend at least O of n time building this hash table. When we get down to this for loop, we can break out of this for loop early, return tuples one at a time in the for loop. So this part is fast for limit queries. It's this part up here that's really slow. And so best case scenario with a limit clause, you're still in an n plus k runtime. So we reduced the m part down to a k, but we still have to pay the full n penalty. One of the, I guess, main takeaways of the hash join is not only do you not need to have an index in order to do the hash join, but there is no way to create an index that will speed up a hash join. If you are in the situation where you're using a hash join or want to use a hash join, the only way to make it faster is to increase this working memory parameter that's fixed inside of Postgres. Are there any questions about the hash join? Okay. I realize this is maybe a little bit on the boring side, just kind of going through the notes like this. What we're going to do next is we'll take a look at the last merge strategy, the merge join strategy. And then once we've talked about all of these and some of their strengths and weaknesses, then we'll switch over to a actual terminal and get some more like practical playing around with Postgres and seeing when it chooses each of these join strategies. So we just have to talk about the details before we can do that. So the next is, and the last one is the merge join. And the way to think of the algorithm for the merge join is it's just like the merge step in merge sort. In merge sort, if you're given two sorted lists, then you can merge them together in linear time. And the pseudocode for doing the merge sort merge is basically just this down here. And this is also going to be our pseudocode for the merge join step. So it has two requirements. The first requirement is just like we had on the hash join. So in particular that we have an equality join condition instead of an inequality join condition. If you do have an inequality, then the only thing that you can use is the nested loop join. But if you have an equality, which is the vast majority of practical join conditions, then you can use any three of these join strategies. The other requirement, which is the more restrictive requirement, is that we have sorted inputs. You can get sorted inputs in a number of ways. Postgres might choose to explicitly do a sort before starting the merge join operation. Or if you have an index, then recall that if it's a B tree index, we can loop over the index to get our results in sorted order. Anytime we're doing an index scan of any sort, index only, index or bitmap scan of a B-tree index, the output always comes back in a sorted order, which makes it great to just plug it straight into a merge join. So that's the what the advantage is right here. If the data is already sorted, then there's no extra construction step. This step right here, you get to skip this step from the hash join. So it looks like that got deleted somehow, but that's what this line right here is intended to say, is that the advantage of a merge join over a hash join is that you don't have to do this expensive creating a hash table up here. That means you don't need to use up any of your working memory. So you can do this with arbitrary large tables as long as they come sorted. And we won't have this penalty where we have to do something expensive before we can start returning rows. We'll be able to start returning rows immediately. So real quick, we'll walk through the basic idea of the pseudocode. Again, it's just like the merging step inside of merge sort. You'll have an index I and j. I is corresponding to the A table, j corresponding to the B table. And so while I is less than m, j is less than n, here are the corresponding A and B rows, the ith row of A, the jth row of B, and then if they satisfy the join condition, output A and B. And you'll see that if you think about it, then you'll get all the possible situations where A and B could be equal to each other this way. So the asymptotic, like overall asymptotic runtime is the same as the overall asymptotic runtime of the hash join. So if you're having to return a lot of things, then it really doesn't matter whether you use a hash join or a merge join. You'll have the same essentially runtime right here. But one of the key advantages of the merge join is when you have a limit clause, then you can break out of this while loop early and you don't have to have any expensive computation up above. These, in practice, these limit clauses are like super useful. So if you say you're Google and you have a SQL query that is in the back end operating your every time somebody types in a search into Google, you're not returning like everything that matches that search results. It always says there's like 10 million or however many things match it. You're only matching the top 10 things that match it. And so in that situation, you're using this limit clause. And so this merge join is going to be really key to getting good performance over the hash join. So yeah, conclusions, main takeaways. The merge and hash joins are faster than the nested loop join whenever both tables are reasonably large. But if only one of the tables is large and the other one is small, the nested loop join with an index is likely to be faster. And then asymptotically, the merge and the hash joins, same runtime unless you have a limit clause. I'm not sure what this, I think this was another reorganization typo. If you do have an index, then that removes the need for a sort step, which would allow faster merge joins. But this line right here shouldn't be here. It should be somewhere else. I'm gonna real quickly take us back to this table over here, the summary of Postgres join strategies. And so what we just talked about is essentially the situations of when you have a good, each one of these is a good strategy, and then which indexes you should create in order to help out your actual joining. From a like actual performance optimization perspective, those are the two things that are really the things that we care about. Are there any questions about these join strategies and what they're doing or what their runtimes are?
I wasn't too sure about what the rechecking and stuff was in the hash.
So this line right here, this recheck. So one thing that can happen with a hash function is that, let's say the columns that we're joining are text columns. And so we have, they're like the hashtags from our Twitter Postgres table. And we have hashtag coronavirus and hashtag USA. So those two different hashtags, but they could, our hash function could combine them down into the same integer value. They could both map to the number 5 and get put in the same bucket. And because of that, when we're doing this, once we've checked to see if the column is in the hash table, all we know is that the hash value itself is in the hash table, but it doesn't actually guarantee us that the columns themselves match before doing the hashing. And so this recheck ensures that not only do the hash values themselves match, but the underlying values before hashing also match. In terms of how much overhead this imposes, it's pretty much negligible. So it's really easy just to even forget that this happens. The really only the main overhead is this line right here. Did that answer your question, Savik?
Yeah, that makes sense.
A good question. Any other questions about the join strategies? Okay, I'm going to switch screen over to a terminal window now, and we'll look at some of the, let's see, so all the things that we were just talking about, they're related to all the true and false questions related to join and join strategies in the homework. What we'll talk about now is about things related to those more free response parts and how to actually create indexes that influence your join strategies. So I'm currently in the PG normalized database. And one thing that I've done is I've modified this database so that there's basically no indexes anywhere. Let me go ahead and drop this index too. The way to delete an index in Postgres is just the command drop index and then the name of the index like this. And now we run this, no indexes at all on our tweets table. And I also want to take a look at our tweet tags table. And you can see there's no indexes on this. Before I made these modifications, there were indexes because recall that every time you have a unique constraint, which is caused by a primary key constraint, that is going to create an index for you. Likewise, anytime you have a foreign key constraint, that's going to create a B-tree index as well. So even though in the schema file, there was very few times where I actually had a create index command, there were many, many indexes that were being created. And in your homework, there are no explicit create index commands in the schema that I give you, but because there are primary keys and foreign keys, there are a lot of implicit indexes that already exist. But here I've taken those away, so we have no indexes at this point. And what I want to do is I'm just going to create a join between the tweets table and the tweet tags table. So we'll do this by select, so we'll get the text of the tweet from tweets, join, tweet tag using id tweets like this. So this command right here joins the tweet tag table to the tweets table and does that on the ID tweets column. So this column right here matching this column right here and gets us the corresponding text of the tweets. I could use a join like this with a where condition, something like where tag equals hashtag coronavirus in order to get all of the text of tweets that have hashtag coronavirus as their tag. I hit enter right now. Oh, let's see. Got a typo right here. Tag should be plural with an S. You can see that this query is taking a long time to run because there are no indexes currently on the tables. One of the things that I commonly do whenever I'm playing around with Postgres and thinking about which indexes I should have or not have, I turn on timing, \timing on. And what this does is it actually will print out how much time every command takes to run. So I'll rerun this command up here again. And I'll press Q to get out of this. And we can see that it took about 1.5 seconds to run. Let's see what the join strategy was. We'll do explain in front of this. And we get this, this strategy right here. So we can see that the parallel hash join is being used. So it's a hash join, and all of these joins can be made parallel in different ways. So the fact that it says parallel out front just means that we'll have, in this case, 2 different workers working on this, this join. And here we're doing a sequential scan on tweet tags and a sequential scan on tweets. The tweets table is the one that is getting the hash table constructed of it. I know that because it says hash right here. And there's no hash table on the tweet tags. And then this part right here is actually doing the hash join. I can disable parallelism temporarily with the command set max parallel workers equals 1. And so now there will be no parallelism. Oops, maybe 0. Okay, I'm not sure why that didn't disable the parallelism. The reason that I was going to do that was just so that our query plan would be a little bit simpler, but it's the same query plan that we'd have otherwise. It's just this word parallels put in front of things. Are there any questions about how to read this, this query plan right now? Okay. So let's think about, first of all, why did it choose to do a hash join instead of any of the other join options? Well, in this case, both of our tables are relatively large. If I want to just see how large, count star from tweets, select. So I currently have 4 million tweets in the tweets table, and from tweet tags, 10 million rows in the tweet tags table. So that's very, very large tables. If I were to do the nested loop join without an index, it would be this times this, which would be an absurd number, take forever. So definitely that's out of the question. The hash join was chosen over the merge join because the merge join requires sorted input. Sorting is an in-login operation, which is bigger than the O of in operation just to create the hash table. So when we don't already have sorted input, the hash join is preferred to the merge join because we don't have to sort it. In order to make this query faster, I'm going to create some indexes now. And the actually, before creating the indexes, let's go ahead and disable the hash join, and we'll see what happens. So set enable hash join equals off like this, and rerun this explanation right here. And now we can see that it's using the merge join strategy, merge join right here. You can see that we're still doing a sequential scan on tweet tags and still doing a sequential scan on tweets right here. It's chosen to make this scan parallel and this one not for whatever reason. But after this sequential scan, we have these sorting operations, and these sorting operations are more expensive than just creating a hash table. And so that's why this was not chosen until we disabled the actual hash join strategy. Put the hash join back on like this, rerun this, there we go. If we look at the estimated runtimes in order to compute these results, you get that the estimated runtime of the the hash join is about half the estimated runtime of the merge join. Okay, so now let's create some indexes. And my goal with these indexes is I want us to be able to use the merge join. I want to be able to use the merge join without having to do this sort step. So in order to not do a sort step, I need a B tree index, because when I scan a B tree, doesn't matter what kind of scan, whether it's an index only, an index, or a bitmap scan, the results are guaranteed to come out in sorted order. And so if I create an index on both of these two tables on the appropriate key, so the appropriate key being the thing that we're sorting on right here, then it can use the index to get things back in a sorted order and not have to do this explicit sort step. So let's start with I'll create an index. We'll do it first on the bottom one, id tweets. Create index, tweet tags underscore idx on tweet tags id tweets, like this. And there's 10 million things in there, so it took a little while to create that index, but it was still pretty fast, less than a second for 10 million items. And now that we have this, so we have a single index, just an index on tweet tags. And so we could do away with this sort right here, but we cannot do away with this sort up here because we do not have an index on tweets right now. So let's rerun our explain command. And you'll see that we still are using the hash join strategy, because even though I've created one index, I only created it on one table. And so I still have to do a sort on the other table. I'll do a set enable hash join equals off, like this, rerun the explain. And now here is the results. Actually, in this case, you can see that it still has an explicit sort right here because it's doing a sequential scan on tweet tags. So I chose the wrong one to do first. But the reason we have to do a sequential scan on tweet tags is because we have this where clause over here, this where tag equals hashtag coronavirus. Our index that we created before, it does not let us solve this portion of the query at all. And so it doesn't let us do this filter. And so that's why we can't do a scan right here. Let's delete this where clause like that, rerun this, and still wants to actually do a sequential scan of this and then sort the results. Did I create my index correctly? Tweet tags and tweets. It looks like I did. Okay, I'm not sure why it's continuing to do this explicit sorting step. I thought I had done this just before class and it took it away. But let's go ahead and create an index on tweets up here and see if we can get rid of this sort. So create index tweets underscore idx on tweets underscore id tweets. So my sort key right here, tweets underscore id tweets, and that's why I chose this value, this table, and this key to do the to create the index on. This is also the primary key of this table. So if I had left in the primary key annotations for the table, then an index like this would have already existed. But because I took that away, I have to create this one manually. And now let's rerun this explain. There we go. It's chosen now to use an index scan on tweets idx and an index only scan on tweets tags idx. Yeah. Are there any questions about how those two indexes I created allowed me to get rid of these sorts up here?
So what if we created a partial index using the where clause and then use that index? Would that allow us to do the same?
Yeah, that's a great question. So the question is, this query that I'm running now is not quite the query that we started with. It's not really the query that we want. And the reason is that I took away that where clause. I took away the where clause just to simplify things for a second. But let's see what happens when I add it back in. Where tag equals hashtag coronavirus, like that. And now what we can see is that it's actually choosing to use a nested loop join, where on the outside of the nested loop, so this is the part that's sort of the for loop, is a sequential scan over the tweet tags table. And then the inner part is an index scan on tweets IDX. So this is I guess, a decent query plan that our sequential scan over tweet tags. Because we have this filter right here, this is going to be a relatively small thing that will, a relatively small amount of things that we're going to do. So it's not too bad having it in the outer for loop, but we can probably do better if we created an appropriate index that would let us do a merge join strategy. So in order to create that appropriate index, here was the create index command that we used on tweet tags. And Satvik had suggested we try a partial index with this where clause where tag equals hashtag coronavirus, like this. Oops. And this error message is saying that this name of the index already exists. So I just have to name this as something else. And I'll just put a 2 at the end of my name over here because it's essentially the same index, just modified a little bit. Hit enter. Happened pretty fast. And now if we redo this explain, then we get that it is in fact able to use both of the indexes. Here, this index scan right here is what we had before. Here, it's using a bitmap index scan to first gather together all of the results from the tweet tags table that match the hashtag coronavirus. That's going to be a relatively small number. And so then it's choosing to use that small reduced table as the outer for loop in a nested loop join. In order to see that this is going to be a relatively small number, I'm going to do a select count star from tweet underscore tags, where tag equals hashtag coronavirus. And before actually running the query, let's do an explain like this. You can see this is an index only scan on this partial index that we created before. And now let's actually run it. And so there's about 9,000 tweets that match this, right here. For Postgres's purposes, it thinks that 9,000 is a relatively small number and chooses to use the nested loop join strategy in order to do that. If we wanted to force it not to use the nested loop, but to instead use, say, a merge join, then we can do set enable, hit tab twice to see the list of things. There we go. Nest loop is the name of the variable that I want to disable off, like this. Rerun this explain command like this, and now we've forced it to use a merge join. We can actually benchmark the how long it actually takes to do these things. So recall that when I use the explain command by itself, it does not actually execute the query. It just creates the query plan and provides these estimates for what it thinks the query is going to take to run. So these here are estimates of how long it's going to take to run. Let's go ahead and do explain analyze now. And so now it's actually running this query. You can see that it took a little while for it to run. And this actual time right here is the actual runtime. This number over here is the one that we're interested in, and this is the actual number of milliseconds that it took to run. If we compare this number to this number right here, the full-on execution time, you can see that they're basically the same thing. This number right here is just the time for executing the query, but then there's the planning time and like other background things, so the actual execution time is a little bit larger. So that was with the nested loop set to off. So it forced us to use the merge join strategy. Let's set it to on now and rerun that same query. You can see that the results came back much faster, basically instantly. And our runtime now is only 131 milliseconds instead of the 2000 milliseconds. So I personally would have guessed that a merge join would have been faster in this situation than a nested loop join. But Postgres knew better. It knew that the nested loop was going to be faster based on all of the statistics that it had picked up. So that's why, in general, we try to let Postgres always pick the query plans for us. It's going to do a good job, and actually in Postgres, there's really no good way for forcing it to do certain parts with a certain algorithm. In other database systems, it's very common to do that because the query planner is not as good, but Postgres is the sort of the best possible query planner in certain formal senses. And so because of that, we don't try to force it. We just let it do its thing. Any questions about any of that? Okay, maybe, yeah, just one last thing I'll say here. I was specifically enabling and disabling these operations just for like debugging purposes to make sure that I do have the correct indexes to do certain operations. But again, in your actual production system, once you've gotten your indexes correctly specified, you don't ever disable any of these operations. You leave them all enabled so that Postgres can do its thing. So that's a full sort of explanation on joining two tables at a time together. In the real world, though, we don't always join just two tables together. And the join strategies that Postgres implements, or actually any database system implements, they're always specialized just to two tables at a time. And so when we want to join multiple tables, we must decide which order to join the tables in. This turns out to have a huge impact on join performance, and it's a very active area of database research. If you're interested in some of the background of that, you can follow it up with this link here. But our takeaway is that Postgres is, again, state-of-the-art, and in certain senses, we can prove that it's impossible to do better than what Postgres is already doing. The only situation where Postgres can sometimes make mistakes is if it guesses wrongly about how many rows are in each one of our tables. So I'll switch back over here, and you can see that in this nested loop query, recall, so I did an explain analyze in this command. And then inside of these parentheses, the first number is the runtime costs. The second number here is the estimated number of rows that will be returned. And then the third number here is the estimated number of bytes per row that will be returned. This estimate right here is the thing that if Postgres gets this number wrong, then it might choose to use the wrong join strategy. Here it estimated 3,000 rows. It knows that's a relatively small number, and so the nested loop is going to be best. If it had estimated, say, 100,000 rows, then it would choose probably a merge join strategy instead of a nested loop, and that's where it's going to choose the wrong situation. Here we can see that this is pretty close to being correct because these two numbers are, I mean, they're a factor of 2 off, but in terms of orders of magnitude, that's not too bad. In order to help Postgres make these estimates, then that's what the vacuum command, auto vacuum, is doing all the time in the background, collecting statistics about all the tables so that it knows how many rows will be returned on these queries before actually doing them. But if you've just done a big insert and you want to tell Postgres to relook at these statistics, then the command is the analyze command, analyze, and then the name of the table, so like tweets like this. And this just tells Postgres to rethink about these things. And now if we redid this, you can see it's, so I had already run that command so that it had good estimates for class, and you can see that it gives us the same numbers here. So from a practitioner's perspective, you just need to know that if you're getting bad queries plans, run the analyze command and you'll get good query plans. Although there's a lot more that goes on in the background of research. Maybe I'll say something too about this website, Cockroachlabs. So CockroachDB is a database that has spun off of Postgres. There's a lot of forks of the Postgres project, and this is one of the ones that's sort of really gaining a lot of popularity these days. CockroachDB is specifically designed for having something that's basically like Postgres, but rather than having it just on like a cluster of machines in a single data center, you can have it distributed over the entire world, and it handles things like relativistic concerns about, it takes a couple milliseconds for the speed of light to travel from Los Angeles to London, and that affects internals of databases, and they're working on handling that. Any questions about anything related to join ordering before we start our discussion of full text search? Okay, so yeah, what we'll talk about next is going to be what you're related to your next homework assignment. So we've already covered everything that you need for your previous homework assignment, and then we'll continue talking about this tomorrow, or sorry, on Wednesday, and get the details of the homework assignment then. So consider this query right here. So we're selecting the ID from the tweets, and we're using this like clause in order to do so. And so recall that in the like clause, these parentheses are like, they're wildcards. They match anything. 0 or more characters can be whatever you want. And so what this query is doing is it's finding any tweet that somehow contains the string corona inside of it. So it could be coronavirus, could be hashtag coronavirus, could be hashtag corona, could be corona the beer or corona the city, anything that contains corona inside of it. And the important thing about this query is that neither a B-tree index nor a hash index can speed up this query. And so let's think about why that is. So for the hash index, we've already said that the only thing that it can do is exact quality search. Like is not exact quality, and so that's why a hash index can't be used. A B-tree, though, is a little bit more subtle. And so let's imagine we change the where clause to be this instead of this. So in particular, notice at the beginning of the string here, I've taken away this first parenthesis. And here, actually, a B-tree can speed up this query. The reason is because this like condition, this thing right here, can be rewritten as this range condition. Any text that's greater than or equal to corona, and any text that's less than or equal, or just actually strictly less than corona B, like this. The word coronavirus matches both this condition and this condition right here, as an example. And we've talked about how B-tree indexes, they support these range queries efficiently. That's one of the things that's great about them. And so B-tree index can support this query right here totally efficiently. So one question that you should think about and be able to answer, I won't answer this in class, is that if we were to replace this like query up here with an I like query, how does that affect our ability to do index scans on this condition? So recall that like is case sensitive and I like is case insensitive. And so if we had a case insensitive query on something like this, is it possible to do that with a B-tree? How do we have to rewrite that with a B-tree? That's something that you should be able to answer. And so these one-sided wildcard queries, they are really useful, but they're not useful for full text search. For our database, Twitter Postgres, the way it comes up as being useful is if you want to find hashtags that start with the word corona, then a B-tree index is able to do that just fine. And you don't need any of this special full text search machinery that we're going to talk about. So what we'll talk about next time, I'll just do a quick high-level overview. We'll first talk about the different full text search systems that exist outside of Postgres. And then we will talk about full text search inside of Postgres. We'll see that it's in particular, there is no SQL standard for full text search. Where's it? That's this right here. There is no SQL standard for full text search. All the things that we've seen so far in this class, all are like generic SQL, can be applied essentially to any database system. The details about how tables are stored on disk, those are things that would be slightly differently, work slightly different, those implementation details, but the interface of the SQL commands are all the same. What we'll start talking about, though, is going to be different in any database system because there is no standard for it. We'll first see just like what these non-standard commands are, and then we'll talk about the indexes that you can create to make those non-standard commands faster. There's going to be 3 of them that we'll talk about: the gin index, the rum index, and the gist index. And what we're going to do is we're going to use those indexes on the Twitter Postgres database in order to re-implement your MapReduce programming assignment, but we'll make it so that you can answer those queries in milliseconds instead of in hours or days. And then we'll also be using these indexes on our final sort of project with that web page that we saw at the very beginning of class to be able to search the whole internet efficiently. So we'll start that discussion next time, and but that's it for today. So stick around for anybody, if anybody has questions about the homework or anything else. But otherwise, I will see you all on Wednesday.